Okay, so now let's move on to scaling transformations. So they're associated to the parameter lambda. In this case, we have one parameter, and we know that zeta mu is equal to uh, minus lambda x mu. So zeta mu, we know, is a length, so is x mu, and that means that our single parameter lambda must be dimensionless. So this means that lambda must be length to the naught. It's dimensionless. Good. Uh, okay. So just to write down, we'll use this below. X mu is equal to x mu plus zeta mu. That's the infinitesimal version of the transformation. What is the finite version of the transformation? Well, the finite version is that x tilde mu is equal to e to the minus lambda x mu. And this is now the finite transformation. So it's just performing a scaling, and it scales each coordinate in exactly the same way. In this formula, lambda can be any real number. Good. Now, we usually call the generator of conformal transformations capital D. So that's conventional notation. It's also conventional to call capital D the total number of space-time dimensions. So sorry about that slight ambiguity in notation, but it is pretty standard. So we can write the generator, sorry, we can write the finite transformation now, as usual, as e to the I lambda d. So this is, again, just using the fact that we are dealing with a Lie group. If it's infinitesimal, so let's imagine we're studying the infinitesimal case, then we can expand this out, keeping only the terms which are linear in lambda. So I've dropped all sorts of lambda squared terms there, but we don't need to worry about those. And we know that the infinitesimal transformation is 1 minus lambda d. 1 minus lambda. Let me just cancel that. We know that the finite transformation is x mu minus lambda x mu. Okay, and that's just by this equation that I've just underlined in red. Now, if we compare these two expressions, the 1 times by the x mu is exactly the same as the x mu. So by comparing the second term of these two expressions, we can figure out what is the equation for the generator. So we learned that I lambda d acting on x mu must be equal to minus lambda x mu. Okay, good. From this, it's pretty easy to see exactly what D is. So let me just write it down. You can easily check this. So we've got an I. Of course, the I is going to combine with the I on the left-hand side to give us a minus on the right-hand side. And then we've got x alpha d by dx alpha. So this x alpha d by dx alpha, you'll remember, it just counts how many x's we've got. So that's the equation for the dilatation operator, the generator of scalings. And, well, you can check that it obeys the equation just above it, boxed in green. So the green equation implies the form of the generator that we found. Good. Now, there's something that I want you to remember, because now we get something interesting with scalings that hasn't happened before. So let's just point that out. So remember, how did we define conformal transformations? Well, what we did was we said under a conformal transformation, the metric should just be rescaled. So if we take eta mu nu, dx tilde mu, dx alpha, let's say dx tilde nu, dx beta. So that was the metric after we changed coordinates. And we said this could be equal to omega squared times by eta alpha eta. Good. And then let me just define all of the quantities appearing here. So x mu, as usual, is just x mu plus the conformal killing vector, zeta mu. Omega, the scaling factor, was 1 plus little omega, and little omega was equal to 1 over space-time dimension, so d is a number here, not the dilatation operator, and then the divergence of the conformal killing vector. And what transformations did we consider so far? So, well, we considered translations. And remember, for translations, we had zeta alpha was equal to A alpha, and this A alpha was a constant. So that was important. So in this case, omega, which is 1 over d, d alpha, A alpha will vanish because A alpha is a constant. So in the case of translations, we don't get a non-trivial scaling of the metric. Capital omega is just 1. What about the case of Lorentz? Well, in the case of Lorentz transformations, remember that zeta alpha was equal to omega alpha beta x beta. And we knew two things. So first of all, omega beta alpha is a constant, but then also importantly, omega beta alpha is antisymmetric. So it's minus omega beta alpha. Okay, so if we now calculate what is little omega is equal to 1 over d. Then we've got d alpha acting on omega alpha beta x beta. Because omega is a constant, the derivative only acts on the x beta, and it will produce for us the Minkowski metric. And this is calculating just the trace of omega, but omega is antisymmetric. So this vanishes. So what you see is, for both translations and for Lorentz transformations, there is no scaling of the metric. And this makes sense. These were both Poincare transformations. And if you remember, Poincare transformations leave the Minkowski metric invariant. So that's why capital omega was equal to 1. This is not just a rescaling of the metric. That rescaling is 1. It's actually an isometry. It leaves the metric invariant. Now, if we look at scaling, now the story is different, because now zeta alpha is equal to minus lambda x alpha. So if we calculate little omega, this is 1 over d. We've got d alpha of minus lambda x alpha. Okay, lambda is a constant again. So let me put that down. Lambda is a constant. So when d alpha acts, it'll act only on the x alpha. It'll give me a delta alpha alpha. If I sum over alpha, that'll give me a d. So that'll cancel with the 1 over d. So that in the end, I just get 1 minus lambda. And then there is some non-trivial scaling of the metric, just given by 1 minus lambda squared. So actually scaling is not part of the Poincare group, but it is part of the conformal group. So this is the first example that we've met that really was a conformal transformation, but not a Poincare transformation. Good. We've got one more transformation left, and that is associated with parameter B alpha. That's called a special conformal transformation, and we'll do that next.